Hey everyone, this is Jason Key from SBGrid. Thanks for joining today. We're lucky to have Lance Westerhoff today. Lance is at QuantumBio. So Lance is going to tell us about MovableType, the fast free energy calculations for drug discovery. Lance, go right ahead.
All righty, certainly. Well, thanks a lot, Jason, for inviting me. I certainly enjoy doing these. I think this is our third one of these over the last several years. The first two were focused, of course, on our crystallography methods that have been in SBGrid now for some time. We've heard from some users, which is great. Certainly, keep any questions coming and that sort of thing. Those tools still remain, and in fact, now we're actually starting to bring these two technologies, both the one I'm going to talk about today and those previous X-ray methods together, actually as one package, and so it's a pretty exciting time. So the methodology itself, this is a paper that just came out. It's under ASAP at JCIM. I think it was probably 3 weeks ago, so it's very recent, maybe 4 weeks ago. And this will be in the upcoming issue that they're having at JCIM on special free energy methods or new free energy methods that's just about ready to come out, I believe. I think it's supposed to be later on this year. We expect it. So certainly take a look at the paper. This goes through both the process that we did for development to a certain extent, but it was really how it was being deployed, and finally how it's validated. I'll touch on a couple key things today, and I'll try to shift this conversation more towards usage and the ideas of usage and rules of thumb of usage. But certainly, if there's any theory questions, I can either handle them here or else, certainly could take a look at the paper, which is also is available under open access, and so you'll be able to download it without a problem. So in any case, in terms of the overall talk, I'll talk a little bit about the overall goals of the method. And that's also gives you some background as to what's going on with this method versus other methods. Why are they a little different? How are they orthogonal? That sort of thing. We'll talk a little bit about the theoretical underpinnings. How all these aspects work together. And the reason why we're going to talk about that, not just because of the science is cool, but also I think it's important for you to understand as a user how all these pieces work together. And when we're talking about confirmation generation, when we're talking about docking or global sampling, and then of course what we're talking about when we're talking about ensemble scoring, all those aspects we'll talk about. And then finally, I'll note an example that again came out of that paper that I just noted, which is also listed at the top of the list of papers at the bottom of the slide here. And then finally, we'll just talk about a mini tutorial or just kind of where you can get some information about how to run this thing on the SBGrid approach or platform. So now what, I guess in terms of the methods, some background, broad strokes, if you will. The method itself is, and again, it actually was beginning to be published. I think the first paper was in 2013. There may have been an earlier one. I don't recall. But in any case, it's the same one that came out of MSU. We have recently in-licensed the method, and then at that point, now integrated with our platform. The key take-home, though, is really that it utilizes both a localized sampling and a global sampling in the form of docking. And so for all the examples I'm going to talk about anyway, they are, you have a set of dock poses, and then you locally sample each one of those poses. And interestingly enough, and I won't talk about this yet, but it is something that you can also do, is you could also just as easily take sample or poses that would have been generated out of microdynamics or other methods as well. We just happen to choose docking in part because it's very fast. And you can very quickly go through a good number of poses that way. It's high throughput, and this again is probably the big differentiator. The end state score, which is what we apply to a single pose, a single set of XYZ coordinates, that takes less than 5 seconds on a regular CPU on a laptop. So it's something that you can do very quickly. That's doing all the localized sampling that I'll explain in a minute. And then for the ensemble, you can generally go through multiple compounds per CPU hour, and it's actually more Docker dependent than it is MT dependent. So you're limited in that case to just how fast your Docker is going to go for the most part. In terms of interoperability, and I've of course mentioned docking a few times, there is a built-in docking routine. It's called the heat map Docker. Again, it was the same one that was published in prior work. But you can also couple it with the third-party Docker. So a lot of the results I'm going to talk about are actually ones that we used Mo to do the docking, and effectively use that, read that in, and then use those poses in place. And of course, the benefit of that is, as we all know, different Dockers have different strengths and weaknesses. And so building this to be Docker agnostic allows you to choose the right Docker for the job, at hand. And of course, as I mentioned, it is compatible with conventional clusters, workstations, and laptops. You don't require GPUs for running all of these. And then finally, in terms of the ability to execute it, you can choose between a command line, which of course is what we're going to talk about today. If you have Mo, you can use Mo. It's not required, but that is what we provide for a GUI. And then finally, we do have a web service version of this then as well for the JSON API. The key take home of all of this is that, again, as it's probably coming clear, is we don't require you to run a whole lot of dynamics or or these exotic or complicated hardware software combinations. It is something that you can very quickly turn the crank through a whole lot of different poses, and then therefore a whole lot of different ligands. So where does MovableType fit in versus other free energy methods? And of course, everybody knows tools like FEP Plus and Amber TI and Lambda sampling and certainly the list goes on. We certainly have a number of tools that are out there, both open source and closed source and everything in between. And it is orthogonal, but there are some similarities. And one of them is both of these are statistical mechanics-based methods, and so they are theoretically complete. You are building a bound and unbound and unbound versions of the ligands, unbound versions of the proteins, bound versions of the complexes. Very similar pair potentials are as an option. You can use an Amber-like force field for a pair potential, or we by default use the GARF statistical potential that was published in a paper from last year, or 2 years ago, I guess it was. And then finally, all of these methods do rely on entire samples, or excuse me, ensembles, where if you are traditionally, if you're looking at a score, for example, just a protein ligand score, you might just have one protein ligand complex. These, in this case, all of the examples I'm going to talk about actually use 25 different poses. And so that's not unusual at all. How things differ, again, is molecular dynamics requires long simulation runtimes. They can be on the orders of days or potentially even weeks. MT, of course, uses this blurring method that I'll talk about in a second, combined with docking in order to mimic or to allow you to sample again in a local versus global regime. And then therefore we tend to have better high throughput. So we can do this in an almost real-time basis on a per ligand basis very quickly. We have good convergence therefore. And then finally, it does end up being pretty easy to use. If there's a setting that you want to try differently, it's not a huge amount of cost to try a different setting. It's not something that you have to wait, potentially, hours to days to find out whether or not your setting is correct. You could try several different settings and see which one fits best for your particular structure and set. Okay, so the overall tool chain, the end state scoring, I already mentioned that, of course, is the protein ligand complex itself. Optionally, you can use the heat map docking that's built in. Conformational search, of course, would be for generating all the conformers. And then finally, the ensemble, which would be scoring 25, 50, even 100 different poses if you like. And then something actually it's noted here as coming soon, but in fact, actually from a scoring perspective, it's already there. And that is being able to use the protein ligand target, both sides as it will moving. where the protein and the ligand are both moving together instead of just the ligand alone. So what are we trying to do with any of these methods? Whether you're talking about, again, dynamics-based methods, MT methods, or whatever, you're trying to sample this energy surface to get an understanding of binding and how well things are binding with one another. So in an ideal world, you go down the right side and you sample the entire space, and you have all the peaks and valleys and everywhere in between all fully sampled. And we know that's something that really isn't something we can do very easily at all, certainly with modern computers. And so molecular dynamics becomes one of those methods that is used, where you'll explore different parts of the whole surface. Generally not too many peaks, but a whole lot of valleys. And you'll try to understand then how well this thing is binding. But that does leave a lot of the surface that we're not able to sample very easily, again, with the dynamics-based method. And so John Zhang, while he was in Kenny Merz's group at MSU, began to work through this type of a methodology where they could look at, instead of treating a single protein ligand complex as we generally do now, again, in a conventional, again, a docking scoring type of method, you'll have a set of coordinates, and those are out to however many decimal places, thanks to, again, the crystallographers. And that's what we use. Pair that together with some docking, and then you end up with a whole lot of different poses, but you're generally scoring a single set of XYZ coordinates. What this local energy surface extrapolation does is, instead of doing this again out to however many decimal places, everything is based instead on distances and pair atom distances, where you'll be looking at each one of those atom coordinates is actually now smeared. And so instead of setting a set of coordinates out to 3 decimal places or whatever, we'll do everything in distances, and we'll actually sample entire distances. And a fundamental assumption here is that all protein ligand interactions can be decomposed into pairwise atom type interactions. And so every pair potential that we use then is just one atom type to another atom type. And so we can think of this, again, schematically, where you'll have atom type A to atom type A. And maybe in this particular example, it'll be 3.6 angstroms. And again, in a conventional sense, in a Leonard-Jones potential or whatever, you would throw that 3.6 angstroms into the calculation, and then you would end up with what your energy is. And you do that for AB, AC, AD, BB, and so on and so forth. What we do instead, though, is instead of doing a single 3.6 angstroms, we'll do a whole bunch of calculations. We actually do approximately 200 calculations per pair, where we'll go back maybe a half an angstrom. We'll shorten that distance a half an angstrom, and we'll lengthen that distance a half an angstrom. And so then we'll do 200 of these calculations. We end up with a whole vector that then goes into the partition function. And then from there, we can calculate the Helmholtz free energy of that particular pose. And again, that's a single pose. So we could put this together with multiple poses, and then we can through a docking methodology, or through even a molecular dynamics methodology, if you'd like to spend a little bit more time generating even better poses, you could certainly do that, where we then put that together with a whole bunch of poses. So again, and generally, unless I say otherwise, all the examples we talk about use about 25 poses. So from that, then this pairing that local energy surface extrapolation, pairing that with docking to now create a global energy surface extrapolation. Again, we do this for every one of these poses, where you'll have 25 of these smearings. And we can represent this schematically, where you have all of these black dots. Those black dots are corresponding to the 25 or so poses that came from the docker. And then the red then becomes that smearing that goes on for each one of those poses. And so now you can see that you can sample a whole lot more of the surface, assuming that your poses are good. Again, if you're garbage in, garbage out, if it's a really poor pose, that doesn't really make any sense at all, it might be one to leave out, or certainly a few bad ones are likely not going to hurt too much of anything. But If you have too many of them, that is something that you want to look at. But in any case, if you have a set of poses in here, you'll generally have some highs and some lows. So now you're actually able to explore not only the low energy valleys, but also a lot of the high energy peaks as well. So when we explore this then from a workflow and how this is being deployed in the pharmaceutical space, we talk again about calculating these absolute binding affinities, where you'll be looking at this whole workflow where you have a target, a prepared target, a set of PDBs. Again, we can do that preparation, of course, within QMechanic, but as we all know, everybody likes to gravitate towards the tools they tend to like to gravitate towards for doing their preparation, whether that's Mo or Maestro or certainly QMechanic. We can do this for the prepared target. We have the placed ligand. Again, that might be the X-ray structure. That might be an approximation of that placed ligand. And that's really at this stage, really just defining where the pocket is. And so it doesn't have to be perfect at this stage. It just has to be close. And that's defining, again, where that active site is within the protein. This then takes two routes. This will go through, do a conformational search. What that is doing is generating a set of conformers, maybe 100, maybe 1,000, maybe 10,000 different conformers of that ligand. And that would be in the solvent sense or the unbound sense. And that generates, again, a whole bunch of conformers. You can, if you'd like to look at them, you can look at the SDF if you like from those. Of course, if you're running this all within QMechanic, you don't necessarily ever have to see that SDF if you don't want to. All of it would be in internal data structures. And the other side of this would be that it's going into, again, that prepared target or place low, either going into Mo, going into MTDoc, going into AutoDoc, going into Glide, going into whatever Docker that you happen to be using. That again can be for generating a set of poses, and that comes out with, again, a set of docked poses. From there, then, both of these, both the docked poses, which would be the placed poses, and the unplaced conformers, and those again would be the ones that we consider out in the solvent. These come together in the MT score. This gives us then the unbound ZL, or partition function of the unbound ligand, the bound PL, which is the protein ligand, and of course then the target itself then becomes the protein partition function as well. This then goes out. We calculate then the pose ensemble score based upon, again, if there were 25 poses in here, you'd use all 25 poses in that score. So in this example that I'm just going to show here very quickly, you have a lot of options that you can choose from. The ones in red are the ones that I happen to choose for this example, and that it would be a rigid receptor docking. Again, very straightforward setting in most docking software. This, again, was all done in Mo. We can also support, though, induced fit docking, where you'd have end target conformers versus end bound ligand conformers. And the one thing we haven't really talked about at all, and in fact, it's something that we're just beginning to do the exploration internally, is doing dynamic snapshots, where you could have, again, end target conformers and end bound ligand conformers that came instead of being from docking, but actually came from dynamics. The other aspect of this, of what I'm going to show here in a second, is that this was done with Mo rigid receptor docking. Again, we could do this with MTDoc. We could do this with another Docker as well. And now you can kind of get an understanding of the timings across the 255 targets that are being considered. And you can see here where the conformer generation is a minute or two, depending upon the ligand. Docking is where, again, it takes more time. In this case, approximately 10, 15 minutes or so per ligand, which still actually compared to a dynamics calculation isn't too bad. And then finally the ensemble score with 25 poses, and that would take, well, again, on the order of about 10 minutes or so to run. So in this set, we happen to choose the comparative assessment of scoring functions, the CASF set. It's built out of the POBBind group, and it's one of numerous sets that are out there. Many of them we've run as well. The nice thing about this is it does consist of 51 different sets that we were able to use within the method, and there are 5 X-ray models per enzyme. Now, what does this give us? This gives us not only the docking process, but it also gives us a good baseline against for doing an end state score on just the X-ray model. And we could do this then, again, across all of these different sets. And we can say, okay, yeah, in this methodology, it works very well for this one, in whether we're talking about the ensemble score or the end state score. And you can see that here where we have across the, or up the y-axis here, you have the Pearson R, leave one out, correlation for the ensemble versus the Pearson R, leave one out analysis for the X-ray pose in end state. And you can see that, again, and we have lines at the 0.5 R in both the X and the Y. So of course, everything up here in the B quadrant is better or as good as 0.5 or better for both end state and for ensemble. And in the A quadrant, that would be one that actually was better for the ensemble than it was for the X-ray, which was very interesting because that really does imply that that you are because you're now treating a whole bunch of instead of X-ray poses, but now docking poses. I should note that in none of these ensembles did we include the X-ray pose. It was only what came out of the docker. You actually sometimes get better coverage of that active site. And so what you really expect to see or hope to see is that these two end up converging, and they do very well. When you see that the ensemble actually sometimes does do better, that implies that that single X-ray pose either had a problem with it, potentially there was just a standard refinement problem, or there are actually multiple poses within the active site, multiple landscape minima within that active site. And then finally we have a few that didn't show as well, either in the or these would be areas of active research. And that is really out of 55. I think there were 10 that were of a questionable nature, but really the majority of them, 38, almost 40 of them, were up here. And then finally, you can also look at in this case would be the mean unsigned errors. And here we're going the other direction, where we want everything down in this quadrant. And here we had 43 of them that were kcal or less, both in the ensemble, again, across the y-axis, and the end state based upon the X-ray pose across the X. And you can see that they, again, were well within an angst, or excuse me, well within a kcal of error for again the vast majority of the calculations. So now for the last section here, now in this case now we talk about the usage process. So I'm told Jason has installed the package on SBGrid. It is available under the same process. If you've ever used any of our crystallography tools, it is actually using the same exact path, or it should use exactly the same path. It is just using our underlying QMechanic software. So, and I should definitely point out that it's highly suggested that you go and take a look at the tutorials. These tend to be very simple, very easy to explore tutorials that just show you how to use each one of these aspects, whether again you're talking about the end state score or the ensemble score, or putting it together with, and again in our case we talked about Mo, but because at the end of the day the language that's communicating between the Docker and our software is just SDF. We can usually support pretty much any Docker. Now, again, that doesn't necessarily imply that every Docker is completely equivalent to one another. What that's saying is that you can choose the best tool for the job. You can go and find the best Docker that works for a particular target, and that's the one that then you can use for the method. And then finally, of course, you can look at the ensemble, running again with no MTCS, with MTDoc or so on and so forth. So all those examples are available in there. The other thing that we're doing too, and this just began, I guess the first one came out on August 24th, so this is very previous, where we're doing these what are called these quick studies, where we'd like to, on an every month, every other month basis, in fact, we're putting one together right now for this month, where we take an idea that someone has asked or that have suggested, and we run through it, and we say, oh yeah, this worked. How did it work? What was the process that we took? And so we do suggest those as well, where these turn into not only, hey, look how it worked for this D3R challenge set, but also we provide the step-by-steps. These are the thought processes that were behind each one of these steps, and this is what we did. And the benefit of that then too is that, as we all know, papers tend to take a good bit of time to get out. This way, it's something we can very quickly turn the crank on and provide that sort of feedback, not only to the person that's asking the question, but also to the community as a whole. And then finally, for our examples, presumably you have the your SBGrid path, so your path to the discovery suite, DivCon discovery suite /bin/QMechanic. That is our executable, our primary executable, because again, our GUI, our graphical user interface, is a Mo-based GUI. And so if you are using this in a command setting, which I think for most users of certainly MT, but free energy methods in general, they tend to like to do things in a script basis anyway. You would have then, here's your protein, here's your ligand. Again, that's that placed ligand, that initially placed ligand. In this case, because we're doing an end state score, this would be the potentially the X-ray structure. You could also, and this is shown in our tutorials, if this is already a complex PDB, we do have a selection language that's there that allows you to also select a residue within that. And then at that point, then you finally come out with your overall energies, your interaction energies, so on and so forth. And then finally, here is your end state score. And you can see here, I think this was on my little Mac laptop. I think it was about 6 seconds or so to run that localized sampling for that single pose. So when it gets to the ensemble, you get a few more options. You get a few more things that you have to keep in mind or turn on. And if you'd like, you kind of, obviously, if you'd like, you can change this end state to ensemble, and it would do it, actually all of this with one fell swoop in one step. But if you do want to provide SDFs from a different Docker, for example, or you want to turn on and off options for doing optimization of the ligand or the conformers, these would be the settings that you would do, or these would be the command line options that you would explore. And again, these are all on the tutorial to take you through it. But the key here is, again, you have their protein PDB. This is the bound PDB, as it were. Here's your ligand. Again, this is the placed ligand, the ligand that's within it. You can also, if you like, put together a list of novel compounds or novel ligands, if you like. And again, it would go through and dock each one of those and provide a score. Optionally, you can choose what pair potential you use. We suggest at this stage you stick with GARF, only because Amber is just, or MT Amber pair potential is something that's under a lot of development, a lot of exploration in terms of where the cutoff should be and everything else for Amber, but it is something that you can certainly explore as well. And for that, you just turn it on, say -H GARF or -H Amber FF14, and that would turn on or off either one of those. Conformer generation, if you'd like, if you don't provide any options, you just simply say MTCS, we would do it internally. But if you have a tool of choice that you say, well, look, I really like how this tool generates conformers. A great example would be if you're working with macrocycles. MTCS doesn't support macrocycles at this time. That is something, again, it's under active development, but it's not at this time. So you might look at a different tool that works with macrocycles really well. Generate a set of an SDF for your macrocycles. You can actually read that in right there, and that would be used then as your unbound conformers. Finally, your MT doc options. In this case, you may provide the SDF again from whether it's Glide or Mo or Autodoc. If you don't provide that SDF, then it assumes that it should generate it. And so All of these methods then are what are called data-driven, where if you don't provide a tool or if you don't provide a file, it'll attempt to fill in the blank for you. And in this case, it would just simply run the internal Docker. And then finally, this is the key right here, is where you're going to turn on the ensemble. And if you did do the end state, then at that point, then it would just be that protein ligand as placed. If you put on the ensemble, then it would go with however many Docker poses you provide. And then this is kind of a final point that it's always nice to have a gut check, as it were, as you know, when anything that's being generated, anything that's being scored, you can publish or print an SDF version of the output, and so therefore you can get an SDF version of your docked poses or your conformers or whatever you happen to be running. And then those then not only have all the conformers and the XYZ coordinates, but it also has all of the terms. You can then read that into another package if you like, or a spreadsheet or whatever to look at in a little more detail. And then just as an example, the top one here is the very clean. This is running mtdoc, just the built-in docking method. And you can see if you have the ligand, the target, the placed ligand. Again, that could also be a selection within the target. That's fine too. And then turn on your ensemble with mtscore. This is our verbosity setting. Verbosity of 2 is always a good choice. And this is the number of cores. Now, this is something, again, being that it's a new method, we are exploring and expanding the parallelism. And so what happens, it doesn't throw an error or anything. If there's any point where it says, look, this part hasn't been parallelized yet, it just simply takes care of it. It just rolls down to a single core. If it's something that is parallelized already, it'll just automatically scale up. And so I would expect that over time, in fact, actually in the short term, this actually will begin to cover more and more and more of the workflow being done in parallel. And this is a threading parallelism. So it's very straightforward for 32 or 64 cores or however many you may have. And then finally, the other example or the other approach is that you are taking docked poses from somewhere else and bringing them in or reading them into the ensemble. This one happens to be using the MoDocker, and you're welcome to use the MoDocker if you have MoBatch. If you don't, then you can always put your own Docker in that place. Now, I should note, again, I think I've probably said a couple times, but the ensemble is built to be Docker agnostic. But really, there's a note here. If that goes away, there we go. That Docker agnostic is really an indication of compatibility, and it doesn't really imply that this method or any method will be equally predictive for any Docker. It's really kind of a key point that the principle of garbage in, garbage out always applies with any method out there. And so if there's a question of predictability, especially if there's a case where you're taking an example that we've published or that we've put together and you're not seeing a comparative predictability with your choice of Docker, that probably implies that there's a problem with the Docker, that there's some issue that's going on there that it's not. Again, especially if this is a case of here it worked over here for Mo or worked over here for mtdoc, but it's not working for, I don't know, some other Docker. That probably implies that you want to take a look at the Docker more than anything. And then finally, once you've run through that docking process, then you just read in, as it says right here, this ligand _doc.sdf. That would be what's coming out of this calculation within MoBatch. But again, it could be some other Docker. Reads that in, and effectively what it is, it's what's called our nexus points. It sucks that into the software, and it treats that really as if the mtdoc process had run. And then finally the mtscore ensemble is turned on, and the verbosity again of 2, and the number of cores in this case I just chose to be 3. Or excuse me, 2. So just some conclusions to wrap this all up. MovableType method itself is a high throughput free energy method. You're looking at generating, or you use a number of different binding modes, conformational distributions of the ligand. I didn't talk about the protein side, but that is also available as well. If you provide like induced fit docking or dynamics trajectory snapshots, if you will, those are all options as well. And so there at that point, then we would treat all of those docked poses, whether it's just the protein, or excuse me, just the ligand moving, or the protein and the ligand moving, we would treat those as all part of this ensemble. So unlike conventional methods, though, it doesn't rely on dynamics. In fact, actually, even a single XYZ set of coordinates is being subjected to or being treated in a free energy manner where we're doing that blurred sampling within that, within even a single set of coordinates. Then you put that together with a number of different sets of coordinates, and you then at that point get an ensemble. Some things I didn't talk about, and this happened to be in this talk, is that we have compared this to FEP Plus for doing the characteristic Schrodinger 8. We've of course worked with others for some other sets as well. It is generalized. You can use it on really a wide range of X-ray structures. The nice thing about it, again, because it tends to be a lot quicker, it is something that you can use to experiment a little bit. As we all know, there's not a huge number of settings that are required for MovableType, but as we all know, for any method, a little bit of retrospective analysis is always helpful, and then you apply those learnings then prospectively throughout your process. And so a great example might be that you have a retrospective analysis of 10 ligands or 20 ligands, and then now you're trying to find the next set. You might want to explore those 10 ligands first, explore some of the different options, whether you're going to optimize the ligand within the active site, or you're going to do the same thing for the conformers, or if a different docker might be better. All of those options, explore that retrospectively, and then apply that learning then prospectively for new compounds. And then finally, all of the results that I've talked about in this talk, and really most of the ones that are in the paper, and certainly most of the papers that have come out both in terms of our website and publication form, were with rigid receptor and flexible ligand scoring. In the most recent version, and this is why there's not a paper associated with it, because it is the most recent version, it also allows a flexible receptor as well. And then, of course, certainly I suggest that you take a look at that paper that just came out of JCIM. The software is, as far as I know from what Jason's told me, is on SBGrid. And certainly, if you have any questions, now obviously if you have SBGrid questions, talk to Jason and his group. But if you do have any questions about usage of the software, certainly drop an email to my support group. It's a good group. They always like to hear from people that are using the software. And they are also involved with the development process of the underlying methodology. And so certainly things that work, things that don't work, that's always very good to hear. And then finally, the key people that worked the most in my group and our collaborating groups for this underlying methodology, certainly two of my employees spent a lot of time with it. We still, to this day, actually, we still work with John Zhang, who's at the Wuhan University of Technology. And then previously, when we had first begun the process of shifting this over, certainly I have to thank Nupar and Nupar Bansal, who I guess now is at Biogen, and of course Kenny Mers for giving a lot of that initial help along our process. And certainly I need to thank the money. Can't do a whole lot without the money. And ultimately, of course, I also want to thank you for your time as well. This is quite a time here in our history as a people. So it's always good to still be able to reach out to people and talk to them. So if you have any questions, I'm all open.
Great, thank you very much. Participants should be able to unmute if you wanted to ask a question. I had a few here from the chat that I can kick it off with, and if I ask your question and you'd like to clarify, or if I do it wrong, or if you want to follow up, feel free. So Florian Leitner asked, can you briefly talk about the components that go into the energy function? Mm-hmm. How easy it would be to customize parameters?
Okay, yes, that's a good question. So, and actually I do have slides for that. So if you just bear with me 1 second. Of course, that's not it. hold on a second. Might be just easier just to bring up the equations themselves. So to answer the other question while I'm looking here, you can put in your own parameters. It wouldn't be in the current version that you have yet. We do have support now for POBBind files and whatnot. So if you wanted to feed in your own parameters, you certainly could. And so because the Amber potential itself is looks very similar to what I'm sure everybody in the call is aware of and is able to work with. And so yes, you could certainly have parameters that are provided. Right now, what happens if you do choose to run the Amber force field is we calculate the charges using PM6. Of course, as everybody is probably aware, that's where we've spent a lot of our time is running different semi-empirical methods. That is how it would calculate the charges. And then in terms of the atom typing and all those sorts of things are all taken care of automatically then underneath. If you wanted to provide though your own POBBind file and whatnot, you could do that again, not on this version, but in the very near future, where at that point then it would just suck it in for the ligand. For the statistical potential, now this is the potential that is, and again, I certainly reference John Zhang's paper from 2018. He really went through a lot of detail about how these statistical potential parameters came up. And again, this is the default. So this is the one. I mean, certainly, again, being a group of experimenters, you're certainly encouraged to experiment, but the method that we tend to talk about most is this potential, where there's 6 parameters that are trained. It was trained using a Bayesian field theory against the POBBind set. I believe John used 2,000 to 3,000 representative structures from that set. And again, everything, all those that D there, that's that distance. In the Amber function, of course, in the Amber parlance, we'd call it R. In the GARF parlance, we'd say D. But they're effectively the same thing, and that is that distance between atom-atom pairs. And we vary that then. Now, when it comes to GARF, we've already calculated basically every pair, and we just every potential pair, and within a cutoff, we've calculated it. So GARF does tend to be a little bit faster than Amber as well, but it is something that you could use either of these potentials. Did that answer the question?
Yes, it did. So, I had one point of clarification about mol2 files. So Ken asked, he said he's a Sybil user. I guess Sybil is no longer around. I don't have a lot of experience with Sybil. Do those files, how do you jump around between SDF, mol2, or using OpenBabel, or what do you use to?
Oh, what do I use? Oh, yeah. I mean, I think most of ours just is Amber, but really, if you had an SDF, that'd be fine too. We just happen to standardize on mol2s, not as that's the only way you can do it. It was more or less that's just how we standardize in terms of our documentation, because initially that's what we used, and so you'd output from Amber, or excuse me, from Mo. Or you'd output from Glide, and mol2 just happens to be a nice format because it had a lot of XYZ coordinates, and it was clear that generally you're talking about a single pose in that case, because again, if it's a ligand within the active site, you're just defining a single pose. But if it's an SDF, that's fine. It just makes sure in that case it's the single placed pose within the active site. But so yeah, that's fine. I think you'd even provide a PDB file that has the ligand if you wanted to. Doesn't really matter to us.
Yes, so I had a question. If there's any more questions, keep them coming. One question that I had was about just a comment that you made, like, it has to be in the pocket, it has to be close. Your Docker has to be, reasonably sane. This makes me think, like, how can we get to kind of lower resolution squishy structures, right? So drug discovery these days, companies are doing, they all want to Glossios to screen all their targets by cryo-EM. They're producing these 3 angstrom maps, right? Like the poses are ambiguous in the structures in most cases. at least from my eyes, right? Like I can see that the ligand fits in the blob in a lot of different ways. Are people coming to you with cryo-EM maps and saying like, can we use your tools to help resolve the, ambiguity in these cases?
Well, yeah, I'll tell you, that's a good question. We are actually just adding, and it's not in this current package yet, but it will be in the not too distant future. We would be able to do a real space refinement, for example, of a pose or a set of poses, and we are pairing it together with MovableType. And so in that case, yes, I think that would be a really interesting scientific exploration. Again, we haven't done that internally with I think what your underlying question is, could you be provided with, a set of XYZ coordinates, again, maybe some initial XYZ coordinates, provide a density, wherever that density happened to come from, and use that as a part of this process. And what would happen, and this is the way we're envisioning it, and literally this is being built right now. So this is a very much of a look under the covers, as it were, as they would say, where when the density comes in, we would use that then as part of this process. And so if when you're doing that dash ligand followed by a mol2, and I'm talking about the place ligand, that's really just telling you where the active site is. That's all that's really doing. But then with this switch, you could turn this on and say, okay, now go ahead and run optimize that, or I should say refine that in this case, refine that ligand within that active site, and then go through and do the docking process, use the density. So you could actually dock within density and do a real space refinement at each one of those steps. Absolutely, that's exactly where we're going.
Yeah, I'm thinking in some cases you maybe use the density only to confirm that the active site is what you thought it was, right?
That's right. Yes.
And then from there you just go right to your Docker. You know what you bound, you know where it bound, even though you don't know exactly what the pose is, and then you can use the Docker and the tools you described today to sort of take off from there.
A great analog, or a great maybe illustrative aspect to that would be that. So right now, when mtdoc runs, okay, what it's doing underneath, and this again is in the publication, so this isn't a great secret or anything else, but what's going on is it's creating what's called a heat map, and that's basically a probability map where we assume, and this is sometimes a good assumption, sometimes not a good assumption, is the centroid of the pocket is approximately where the ligand's going to live, okay? And so what we do is we build a heat map, a probability map, within a few angstroms of that centroid of the active site. And of course, as we all know, that's not always a good assumption. Either your ligands may be off to the side a little bit, or it's maybe pulled in one direction or another. And so, and on top of that, you might be wrong on some of what your pocket residue definitions are. And so what we're doing instead then, when density comes in, it would suck the density in and then say, okay, instead of using the centroid, we're going to use maybe the difference density as a definition of where to dock instead. And so that actually becomes then the parameter, or the boundary, as it were, for the docking process. And then again, like I said, if you turn on then the optimization, in this case, again, because it's density, we'd have the density there. It's no longer, even though it says opt, it's no longer just an optimization. It'll do the real space refinement then too. So, yep, that's exactly where we're going. So,
we have one question here from Pete Meyer from the group. So, Pete, jump in.
Hi, so this is more going back to a possibly newbie theory type question, but could you say a little bit about where the entropy component of the free energy calculation comes in?
Yeah, so for any of this that we're, again, with any of these types of calculations that we're running for, again, whether we're talking about GARF or AMBER, or if we're talking about, whether it's even the end state calculation, what we're doing is, instead of just calculating a single pose or a single set of coordinates, which effectively has just an assumption of nothing, no movement, nothing whatsoever. In this case, then we would be calculating a whole bunch of poses. And so we might, you know, it's effectively, you can almost think of it as almost an infinite when you start pairing these distances. So you would vary each one of these R's. Instead of running a single, you would run a whole bunch, right? So you would do 200 for every one of these R's or D's, as the case may be.
So this goes back to like the vector in one of your earlier slides, where instead of
Correct. And so you put that together then with, and something I didn't really talk about then was the underlying volume then too. So we would have then an idea and that's basically, it's what's called a linear volume. So it's, you're talking about every atom pair to atom pair. You count up the number of possible pairs and those sorts of things. And so this ends up being then, you know, how we would then get that, you know, both the enthalpic term and the entropic term. And the other term I didn't really talk about at all in this, just for the sake of brevity, was a solvent term then too. And so we do the same thing then for solvent as well, where we would, you know, again, not just sample a single position for water, but we effectively sample an infinite implicit solvent model.
Very cool. Thank you.
Yeah. So and all that does come together. And like I said, I happened to skip this aspect just to make it a little quicker, but that was
Yeah. Well, you had the footnotes, and really I should probably look at some of those papers when I have the time to find some more info about it. But
oh yeah, certainly. Yeah. Well, like I said, let me know that one paper that just came out last month is probably a good starter point, because when we wrote it, we really did try to, you know, kind of go towards the folks that maybe didn't have the background quite yet.
Great. Thank you.
Great. Well, with that, I think we can wrap it up. Lance, thank you very much.
Great. Well, thank you. And certainly if you have any questions, let me know. I'm here to help.